This conference will now be recorded.
Okay, good morning, everybody. Welcome to the OCP HPC sub-project meeting. Let me turn my my camera on. So good morning all. So today we're going to continue from last week's discussion on actually getting started with some of these modules. So I was going to jump in there and focus on the two that we've got most traction on at the moment. Just let me share the screen actually. So you've got the share my primary screen. Okay, good. Yeah, so just focus on the two modules, the IBM Power 10 module and the Xilinx VP 1802 module that we briefly discussed last week. I'll wind back to just the actual top level architecture that we started with, and I'd like to try and start putting some meat on the bone of what we actually need to do to make these modules come to reality. I see we've got in terms of attendees, we've got a new attendee, so welcome Todd Rosedal and from IBM, and I don't see Brian on at the moment. Maybe Todd, maybe you could ping Brian as well if you don't mind. So yeah, we'll touch on the IBM one, and also we'll do that in the first half, and then we'll move on to the Xilinx module in terms of trying to see if we can look at and make a to-do list of how we get these projects kicked off. So that'll be great. But before I do get started, we've got the usual introduction to new attendees. So I believe the only new attendee is Todd. Oh, I guess Chris Poach was last week, but I don't think I gave you a chance to introduce yourself, Chris. So would you like to just, Chris, you go ahead first?
Sure, yeah. Hi, I'm Chris Poach. We work with Programming Log. We have the Load Slimmer brand. Roger Beeston's the owner, CEO.
Okay, great. And you've been helping me look at how we test the power supplies on these modules, right?
Exactly, correct.
And they've also been helping out with some 3D models. If for those of you that attended supercomputing, we had a panel session where we were discussing the HPCM, and Roger Beeston is Chris mentioned, the CEO of Programmable Analog, was on the panel, and he was showing some of his work there and what they could do on the power front to help us from testing of the power modules. Okay, thanks, Chris. And Todd, would you mind doing a quick introduction?
Yeah, sure. Also note that Brian did join just now.
Yeah, great, perfect.
So yeah. So I work for IBM. My past role was in power and thermal management, trying to squeeze as much performance out of the processors as we can. Also doing just standard server power and thermal management, and then the baseboard management controller roadmap. So owning how do we get data out of this system, out of band inventory, fault management, and do all of that out of band functions. I've moved to a new role, which is under Mendy. Most of you probably know, and this is into open source business development. So my plan here, the goal is to try to get IBM is more involved in open source projects, try to support these from both an open power foundation perspective and then from our own enterprise server division. Get us into the open source world is more and more. I think that's the way of the future, and that's the way companies are going to be successful. So my role here would be more on the out of band management of the HPCM. What do we need to do? What are its connections? How do we integrate it in with the bigger with the bigger system, with the system management entities and all that.
Perfect. Thank you, Todd. That was a good introduction. Did I miss anyone else? Is there anyone else new that hasn't introduced themselves before? No? Okay, great. All right. So we'll now move into the discussion on the modules themselves. So let me just move this window out because I'm going to switch over. So I'm going to need to.
Well, would you want Brian to introduce himself too, or is he not a new member?
Brian's been a regular attendee over the years.
Perfect.
But okay, I'm going to put this into. Actually, I won't put it into presentation mode. I'll just go straight here. So just as a reminder, hopefully everybody can see this. Just as a reminder, we were talking about AI applications and the insatiable need for memory and more of these data-centric systems as well. And so what we did is we put together a couple of different scenarios of recreating supercomputing nodes. So this was a recreation of the Summit node, but with FPGAs instead of GPUs, and using the IBM's Power 10 instead of Power 9. And then this one down here was the AMD, which is the new frontier supercomputer that's just going online now. So this was to try and recreate the AMD architecture using an OAI chassis with an OCP server and some AMD MI200 modules and Xilinx FPGAs as well. So today I wanted to focus on this one. So to make these two systems up, we just need 3 module designs. We need the IBM Power 10, we need the AMD MI200, and we need the Xilinx Versal FPGA. And in the case of the AMD system, we'd also need an AMD OCP server that connects to the OAI chassis as well, if that exists with Genoa going forward. I don't know. This was just a hypothetical that if this comes to reality or not. So so again, I'm going to focus on this one. Can we recreate the Summit machine architecturally and well, actually significantly improve on it as well, obviously with latest processors and even better, more versatile interconnect in the OAI chassis, and this would fit into the OAI chassis ideally. So that was going to be made up of 2 modules. So I think I briefly showed this modular architecture of the Power 10 with its various interconnect. So I won't go into that right now. I'll come back to that in a moment. And I did show the Xilinx FPGA one. I did show this generic diagram. And I think we'll come back to this. So in terms of the IO allocations, you've got very generic IOs. A nice thing about Xilinx FPGAs, but the PCI ones do have hard IP with them, so they're called out differently with the blue lanes. And I showed an alternative configuration for the Xilinx module. So it's what do we do with those PCI lanes? So hopefully we'll touch on that on the second half of this meeting. But I'd like to get into the Power 10 one right now. So I think I know Brian's got to drop at the bottom of the hour. So yeah, Brian and Todd are both from IBM, and so they've helped me over the years. And so in putting this together, I'm working with them and others in the Open CAPI work group. So and the Open Power work groups. So I've pasted the diagram again in the top right hand corner there, and I put the labels of, if you remember, obviously HPCM starts out as a protocol agnostic on all of the IO interconnect, and then it gets protocol specific when you put your device in there. So by putting a Power 10 in there, the buses that come out of Power 10 is a proprietary SMP bus from IBM, and Open CAPI, which is the open version, I guess, of the SMP bus, and sometimes some of those buses are switchable between SMP and OpenCAPI. Then it has OMI as its primary memory interface, so it's a serial memory, and that's why this is a great candidate for our module, because again, for those of you that aren't aware, we cannot support parallel memory. We can only support processors either with HBM on board or with external memory via serial links. So the Power 10 is the only production chip that I know of that supports serial memory. Obviously, we've got CXL coming down the road with the other processors, and obviously GPU support HBM, etc. So this is a good candidate for external serial memory for us to start with, and that uses the OMI interface, the Open Memory Interface. And finally, they've got 32 PCA lanes on the Power 10 as well. So that's the configuration of that one. With regards to the OMI, because we are standardizing on the E3 module standard, OMI today is available in production from all the memory vendors in the JEDEC DDIMM differential DIMM format. So that's similar to, but not fully compatible with the EDSFF E3 format. So in OpenCAPI, we already have this design, this dual OMI E3 module in process, in development, that will plug into this Power 10 module. So you'll be able to get a total of 16 channels of OMI, which is the maximum that Power 10 can support and that's at a terabyte per second into this Power 10. So that module design is underway, and I'd like to acknowledge that's in OpenCAPI, the consortium there. Acknowledge support from IBM, TORMEM, Microchip, and Smart Modular for us to actually make progress and make this happen. So that's a critical piece, this module, and like I say, it's already underway. So if we just stare at this is extremely simple in a lot of ways. Everything just comes out to connector I/O. So the only piece, well, I say the only, they're important pieces. The pieces we need to get onto the module, and obviously real estate is a premium on these modules, is we need to get the power in, the power management, the system management, and including the clock tree and the BMC. And so on the BMC front, I'm not really an expert. I know the buzzwords, and I've paid a little bit of attention to what's going on. But OpenBMC is obviously core to OCP, and the nice news there is that's core to Open Power as well. So there's a lot of commonality there. Everybody's trending towards OpenBMC. And there's this new effort called LibreBMC, and maybe Todd will be able to articulate the differences or the commonalities. But I think that was brought in from Open Power and is being adopted inside OCP. And then we've got the DC SCM, the security module, which is a separate sub-project in OCP, looking on the sideband management and the security of the overall OCP systems. So we need to somehow bring this support in. This module at the moment doesn't support a DC SCM module. That uses the same connector but has completely different I/O. It's all just sideband I/O. And I don't really want to sacrifice one of our connectors to natively plug in a DC SCM, but maybe we have to. So that's a discussion point. And just while I'm on the BMC side of things, I think that both Lattice and Xilinx are being used for the open sourcing of this technology from a hardware perspective. I've chosen Lattice here for a couple of reasons. They do the really tiny devices that we need on this board, and they have extensive I2C IP, and we've got lots of I2C buses. We've got at least one bus for every single one of these connectors, and they do a lot of bus aggregation IP that they've got in their devices. So at the moment, I'm favoring that approach versus the Xilinx approach. But that's up for debate if people don't think that's the right way to go. And then on the power management, we've only got 48 volts coming into this. And that's the power modules in the industry are, I guess the 48 volts has been coming for a few years now, and certainly in this module world, Vicor have led the charge there, and I think it's Vicor on every OEM module or every like the NVIDIA SXM modules. Vicor seem to be everywhere in there, so they would be a good choice. But I know that others like MPS are working on or have 48 volt solutions. So we've got some choices there on the vendor options there, and if we can get one or more of them to collaborate on helping us on the power front, I think that would be good. The nice thing about this, we've talked about this module being supporting up to a kilowatt, but this particular module is going to be well under 500 watts. So our power challenge may be a little bit more forgiving than if we were hitting a kilowatt level. So so that's the highlights. I guess what I'd like to do here is hand it over to you guys and say, you know, and maybe Todd, you can maybe kick off, and or Brian, in terms of your view. You know what's needed for this Power 10, and so maybe you can pass comment on some of this. But maybe the first question to everybody is there something I'm missing on this? Should there be a bullet on here that I'm actually missing?
Well, I guess I don't see a bullet missing at this point. What I could do here is go through, you touched on those three, OpenBMC, LibreBMC, and DCSCM, and kind of give an overview of what, the differences between those, what each of those are, so we have a common understanding. Would that make some sense?
That'd be great. Yeah.
Yeah. So, yeah, three projects that are very, very similar. They share a lot of, they share amongst each other, but they are different. So OpenBMC, that is the initiative out there for providing the BMC code open source, completely open source. So IBM started this long ago, and now it's really gaining traction in the industry. We are using OpenBMC on our power servers, most of them now. We started with the AC922 for P10. It'll be the OpenBMC code stack has been enhanced to add enterprise class functionality, and it'll be on most of our servers. And then going forward, it'll be on all of them as we go through time. Intel, Dell, Lenovo, a lot of people are contributing to this, and it is becoming the standard for it. If you have a baseboard management controller in a server, then generally you're going to put this OpenBMC code stack on that server. So that's a kind of good success story from an open source perspective. Now you go to LibreBMC. So that's a project that takes that a step further. OpenBMC says, hey, all of the soft, all the firmware there on the BMC is open. LibreBMC says, well, we're going to go a step further than that and even make the hardware open. So instead of using a standard BMC hardware like an ASPEED 2500 or 2600, LibreBMC project says, we think we can do this with an FPGA and emulate the hardware, the ASPEED chips, or implement it, I should say, on an FPGA. There is so in the LibreBMC project, there's a proof of concept that's been done. We proved that an FPGA can boot the AC922, and now the next step is to have that done more formally, and then also support the DCSCM standard and the DCSCI interface, which I'll get to next. So there are a lot of security problems using a BMC that is an off-the-shelf hardware. You can't see what's inside that ASP. You don't know what that root of trust is really doing. And in this new era of security, you really need to be able to see what your hardware is doing as well as your software. And then this kind of plays into the root of trust. There is a root of trust on the BMC, on those ASP BMCs, but we would either pull that into an FPGA or put a separate root of trust on there. So that's another sort of offshoot here that needs to be considered. And we need a good root of trust, an open root of trust solution. Then the DCSCM, that's an OCP project that is trying to standardize the connection between the BMC card and the planar or the HPM board that has the processors and memory and everything else on it. There was a 1.0 standard that's out right now. It's a 196 pin connector, I think. something like that. Then the 2.0 standard is coming out in April is the plan as we go through and get that finalized. But that would then say you could take buy hopefully an off the shelf DCSCM card, plug it in, and it would support this DCSCI interface. Then put a load on it that then knows you have to know, of course, what your HPM is on the other side, if it's a x86 based or a power based or whatever you're talking to, but be able to put a load on that DCSCM card and have it do in a standard fashion all the functions that you would need to do from a BMC perspective, which would be booting all of your chips, however that's done on that particular system, and then also having all of your out of band management, accepting power on off commands and getting inventory and all that good stuff. That's another thing. And what's going on here that that connector's kind of big. It's because you have to. It's trying to sort of be all things to everybody. You have to have all of the connections that you would have on an Intel and an AMD and an ARM and a power system. And some of those pins are overloaded, but it's still pretty big. There was a new thing called LTPI, which is a serialized interface. The goal would be going forward in the future, you could skinny that connector down and serialize these signals, most of them anyway, because you don't really need a lot of parallel interfaces there because it's not high, and those are not high bandwidth interfaces in general. So you could go through and serialize this.
Hey Todd, that's the lattice one, right? LTPS.
Lattice has an implementation of the LTPI interface. Yeah, they showed at the last conference. But in general, it's just a specification that says how you do this.
Yeah.
So it stands for LVDS, transport protocol interface. And but yeah, so you take all of these parallel things that you would want to do on the BMC, skinny them down, serialize them across that LTPI interface, then blow them back up, and then on the HPM board do what you need to do. So
hey, just on that, Todd, one thing that drove me crazy about the DCSCM was how I guess that's not really going to help us that much, but was how it leveraged the EDSFF connector, but then completely annihilated all the electrical. So if this is going serial, perhaps they could try and use the same serialized pinout sort of thing. Again, it would then fit nicely in with this in this approach. But anyway, that's a side. That's a piece.
I agree with that. I think the way this needs to go, quite frankly, is to get rid of all of those parallel interfaces.
I mean, it's where the I2C is a nightmare, right?
Yeah. Oh, some of them, you might need PERST. You might need some of these that have really timing sensitive things. You might have intrusion pins that need to be parallel. So there are some, but what we need to do as a work group is get this down. And that's after, this is not even part of 2.0. So 2.0 is saying we're going to put LTPI on it and have all these parallel interfaces, and you can kind of do what you want.
Right.
I would like to see the 3.0 go to what is the bare minimum you need for these parallel pins, get this connector size down, do everything over the LTPI. And there are actually 3 of those in the standard. There's LTPI 1, 2, and 3, which have specified different bandwidth and latency requirements. So I think that's good. So you'd be able to say, I can still use LTPI, but I got some really high bandwidth or low latency things I need to use, and that would go over this LTP1. LTP2 would be my lower latency collective EPD or whatever you're going to do. So I think that's the way it's going to go, and we should be keeping that in mind here as we think about how to do this out of band management on the.
Well, I think this will be a good practical use case of this as well, and because this to me is the toughest piece and I'm in a bit of a quandary as to, do we plug in something like a DCSCM module, or what can we actually get into this module as native, and could we contribute that back to these 3 groups?
I'm thinking about this a little bit last night. I mean, I think, if we put an FPGA on here and we, have that be the BMC, do the Libre BMC approach. It's an FPGA, it implements the BMC function, use OpenBMC on it. Most of that can be kept sort of on this HPCM, on the module. My question is, what I don't understand about this is you've got this HPCM, and now you're going to plug it in to a chassis, and that chassis is going to provide you the 48 volts, and it's going to provide presumably some cooling to your module. What is that? What chassis are we targeting, and what is that interface there between this module and the chassis?
Yeah, that's possibly where I need to get. So I need to get you a bit more up to speed on that. But effectively, are you familiar with the OAM chassis, the OAI, or
No,
not?
I saw it. I watched your pitch and you mentioned it, but I didn't have time to investigate
Okay,
what
yeah.
that
So
really is.
it's essentially there is no motherboard. We bring the 48 volts in through two large pins, but the idea is, and it's completely cabled because there's no motherboard. So it would be cabled to a frame, so you could slide this into the OAI chassis and connect into the rest of the OCP infrastructure through the OAI chassis. That's the idea.
That so that makes sense, but when you cable it into that OAI chassis, what are the signals that are running across there? I mean, that's defined in the standard, I
Yeah,
suppose.
there's what they call a host interface board. Now, the OAI chassis is designed that there's a big PCI switch plane called the host interface board, and that connects all of, I mean, so the OAM today is viewed as an accelerator expansion box. It's not, people haven't thought about putting processors in it, although Siamac Tavelli, who led the early efforts of the OAM, said this is a heterogeneous processor box. There's no reason why CPUs can't go in it, and I completely agree. But today, people see this as the backplane that you slide into, which has has PCI switches on it. That gives you your bridging connections to a server box above. And so the processors sit in a standard server and they cable down to this accelerator. Now, by us building this Power 10 module, we don't need to go via the host interface board, because the host is now one of the modules in the chassis. But the key thing is, these modules all talk to the same host interface board, which is a bunch of PCI switches. So you have, this could be the root complex of all the PCIs. Effectively, that will, so you could service all the other accelerators if you wanted to do it with standard PCI enumeration to get everybody, just like you do your normal server, but through this. So I can. But it's a very good question. In fact, as I'm explaining it, I'm realizing I haven't thought about it too much, but I don't see an issue. And so I'll bring you up to speed on that, Todd. And then if you see any other big gotchas that I'm missing, then we can do that maybe offline.
Okay, so yeah, so presumably because it's just an accelerator designed as an accelerator expansion box, you would have the processor and the host on the other side would be the thing that would be
That's right, on
monitoring.
the other side of the host interface bus, but
Yeah,
effectively all that is PCI cables coming out the OAI box, going to a box above that has your server processors in.
yeah, and that entity then would have the out of band interfaces to whatever the system management entity is out there that's collecting the inventory and doing the fault management.
Right. So we could go to a real host that is connected like that, or this could be the host inside the module. Is what I'm wondering.
Yeah, it makes more sense that I guess that this is the host, but there's going to have to be a connection here from obviously from this HPC module out to whatever this entity is, and yeah, you could go back.
The PCI lanes will be the connections for that for sure. Yeah.
Okay, so the PCI lanes that go back to the to the chassis will be that link.
Yes. Yes. Yeah.
Okay.
That'll be so. So the way I'm envisaging it right now, you've got the 16 lane one here. These are the 32 lanes of PCI off of the Power 10. So you've got 16 going to one slot, and the idea there would be you'd plug in a NIC 3.0 here, which would have a Mellanox card or whatever, giving you network traffic out to the outside world. And on these two 8-lane ones, you would go to the back plane and go to the PCI switches on the host interface board. So therefore, this would go to a wider switching network, which would include connecting PCI-wise to the other modules in the same OAI chassis.
Yeah. Okay.
Yeah.
We should draw a picture of that and just at a block diagram level and just make sure this.
Well, actually, here it is. Sorry, this is it. So this switch here is the host interface board in the OAI chassis. This PCI Gen 5 switch.
Yeah.
And
Okay.
you can see that, well, I've shown here all of the lanes go into the Power 10. And then I've shown 8 lanes go into each of the FPGAs. So that's how I've configured the chassis with the Power 10. And then these on the left go out of the chassis into a server, typically to a server chassis, or even SSDs or whatever. So, and there's a nice presentation actually. Facebook gave a nice presentation of showing they have even more PCI expansion with lots of storage, and you can sandwich these together in chassis boxes.
Yeah. So now one of these would need to go out to some other entity that would be this out of band, power off management entity, versus going back to a server where these would only be active.
Okay. So could one of these Power 10s be the root complex, but still have an out of band management externally via the outside the box, or is typically the primary server also the out of band manager?
Well, yeah. So I mean, if you think about it from the perspective, you plug this, take a standard server, going back to that world for a second, you plug it into the wall, right? So now you've got your BMC is up. None of this Power 10, none of this complex would be up and alive. So you wouldn't be able to use that. You would have a BMC that would be alive. Again, it would be talking back to whatever. We have in Power, we have an HMC, or you have some other management box that then says, hey, give me your inventory. That goes to the GUI. Hey, power on, power off. So we would need something on standby. So I think to have these, like you see these FPGAs, to have one of those then act as the BMC. I think that's the Libre BMC concept. That would be good, and it can do all of the stuff that it would do on the host side. It can power all these chips on and off and talk to the VRMs and collect the inventory. But then I'm just looking for that connection from that BMC that's on this module back to wherever it's going that is actually the manager. Yeah.
I mean, ideally, I'd like this to be usable as a standalone box. You say, well, I've got my CPU, I've got my accelerators, and all in a standalone chassis would be fine. But equally, if you're part of a bigger system, obviously from an HPC perspective, you are, then you have this much bigger resource manager, out of band manager, which could be outside of the box, and maybe even a dedicated chassis for that.
Yes, right. That's how you would do it in an HPC. If you think of Sierra Summit, right? That's the way you do it. You have another box out there that handles. I think we have 300.
Handles all of them. Actually, Todd, because we are an HPC focused group, I think probably that is the use case we want to prioritize. But it would be nice if we could do standalone as well, and everything's contained inside this box. If it's just the configuration we're looking at right now.
Yeah, but even I would say that I agree with that. But even standalone, if you take a standalone little mom and pop server that we have, there needs to be some out of band standby entity, because obviously you have to power it on and off. You have to say, well, that my KEC didn't, the chips didn't come up. What's wrong?
And actually, that feature may be in the host interface board as well, possibly. They may even have a DCM support in the host. So I think we need to probably brush up on where they're going with the host interface board in the OAI chassis. But
yeah, good. Okay, that sounds good.
All right, no, that's very good input there, Todd. Great.
Alan, I have a couple of questions actually.
Yeah.
So you in this picture, we're gonna have the dual OMI E3.S module based on OpenCAPI. So
yeah, it's the open memory interface.
How about I just want to know your idea about like CXL interface based E3.S module.
Yeah, no, well, see, you already have your CXL module, so this just brings OMI mechanically into the same domain. Obviously, IBM Power 10's memory interface is OMI. It's not parallel and it's not CXL. So this is so that we can use this in the IBM Power 10. Obviously, if you dropped in let's say an Intel CPU in here, which maybe has HBM on board and CXL, then all these channels would be CXL, and we just plug in the Samsung CXL module, and we're off to the races. So what I'm doing is, because the open memory interface is already available in a JEDEC differential DIMM format, okay, and but that's not compatible with what we're trying to do here. So whereas CXL and Gen Z already have modules from you and Smart Modular have a Gen Z E3.S module. So you know, it's clear the serial memory standards are trying to align with the mechanical form factor of the storage world, and which is all, they're all coming together under this new EDSFF form factors, E1 and E3. And so what I'm doing here in OpenCAPI is we're saying, let's come and join the EDSFF party with the open memory interface, which is complementary to CXL. And by the way, Michael, you make the OMI DDIMMs in volume for IBM already. So Samsung are already well vested in OMI. I'd love Samsung research department to help us build this module, but but you guys are not interested unless there's 20 million, which we're not going to be doing. We're only going to be doing a few handful here to get the idea going. But yeah, if you can get Samsung's interest, then in helping us on that front as well. But yeah, so what we're doing here in this work group is we're making a module standard that's completely agnostic to the interface. So if CXL takes over and everything turns into a CXL port, we're here waiting to support it. Samsung already have a CXL.mem module. You can go to PCI, we can plug in SSDs. SSDs are in the EDSFF format. So this is not, as a work group, we are not trying to say any bus is a winning bus. We're saying we want to support every bus. And
understand.
yeah, so IBM have their own proprietary bus called the symmetric multiprocessing bus to connect. So because they've got those IOs on their device, we're wiring them to the connector. If I put an NVIDIA module down, there will be a lot of NVLink ones on these connectors. And I could potentially cable an IBM SMP to an NVIDIA NVLink, and it would be a disaster. It wouldn't work, obviously. But this part of our system management effort will be, to Todd's point, when we turn on, or before we turn on, the system management says, hang on a minute, you guys are trying to make an SMP bus talk to an NVLink bus. I'm not turning you on because that's an illegal connection. And then you've got CXL, and then you've got Intel's proprietary UPI bus. You've got AMD's proprietary Infinity Fabric bus. I mean, everybody's going proprietary. It's a nightmare. And we've got CXL, which is a second-class citizen to the SMP buses, trying to stitch things back together. OMI is focused purely on the low latency memory channel, the open memory interface, and it's a serialization of the low latency DDR bus. And so it's very complementary to CXL. So what I'm trying to do is say, you can plug in CXL modules. If your processor wants CXL, you can plug in OMI modules. If your processor wants OMI. And on the FPGA, for example, you can plug in either, because the FPGA, you just configure the port to be OMI or CXL. So we could plug an OMI module in here and configure the port to talk OMI. We could plug in the Samsung CXL.mem module in here and then configure the port to talk CXL. So that's the beauty of the versatility of this approach, is we're not trying to pick a winner. I hate, but we've got a proliferation of buses, which is making our industry even more challenging, and stovepiping all the incumbents. And I'm trying to unstovepipe the incumbents by making all this open.
Okay, I understand. Thank you. Can you move back the original,
Hey, Alan.
slide?
Yeah. There's this one here. Is that what that one you want, Michael?
Yeah, my second question was, the OCP security group. They are talking about this, the the system management interface based on I3C this day. So
Oh, I3C, yes, good point.
yeah, so I'm not sure, do we have to consider that one or not?
No, absolutely. No, absolutely. Good, well spotted. Yeah.
One of the things I might add in here is that you can do communications along with the power. Power is usually viewed as just a sort of dumb interface where you just get voltage and current, but you can put in like a fiber comms there. When you're trying to bring things up.
Okay. Well, what do you mean by that?
The one connection everything has is power, but people
Right.
just usually view that as a dumb thing. But if you got the connectors, you can do things like run inert communications like fiber along with power, and it's safe. And you can do that now for HPC type stuff where you've got the money to burn on it.
Right.
Just say, okay, I've got to do some of my bring up management through the power buses rather than using these big data buses to try and configure things.
Okay, actually, that's interesting. I did have some concepts of some sort of optical communication for the high speed sidebands.
Yeah,
so,
I'm trying to do a whole smart home thing with like DC power buses, which you put fiber in the cables because you can do that. You can't put like a Cat5 cable in with the power for safety reasons, but you could put it in fiber, and that's probably a good way to organize bringing things up.
Okay.
But you're not talking about running an AC signal on top of the DC.
No. You got to. It's a physical cable for the power.
Yeah.
It always has to be. But then it's usually high voltage, which makes it a little bit dangerous. But that doesn't impact on fiber. Fiber's inert, so you can run as many fibers as you like with a power cable.
Yeah.
So the only thing there is we've got bus bars. Obviously, we don't have cables, so you'd have to run the optics in the bus bars somehow.
Yeah, it's more that it goes through a socket somewhere. There's a socket for the power into the machine. There's a socket, from the motherboard into the boards.
Fair point. Yeah.
Just one optical connection with cheap fiber in there would help you.
But that would need to be defined in that OAI spec, right? I mean, because if you're saying you cable it back to the chassis, then maybe
I've seen patents where you do things like you drill holes through the power, the plug pins, and feed fiber through the same. You've got mechanical support because you have large blades for the power usually.
Yeah,
so
yeah.
you can make them hollow and run fiber through them. I mean, I've seen somebody's patent for that.
Right. And you're going to need there must already be some communication channel defined there in the OAI spec.
It's kind of a dearth. There's a dearth of it. I was thinking it'd be nice if I just had a PC power supply with like an Ethernet and USB adapters on it, so I could just control my standard PC power supply remotely. But nobody seems to do it.
Well, I need to get up to speed on what those communications are on the OAI because I don't know how it's done. Because there has to be today some how does the chassis and the actual system back that's running on somewhere else behind the chassis, how does it know that this blade is dead, that accelerator isn't working, the 48 volts didn't come up or whatever? There's got to be some way that they've already are doing that. I suppose what it is.
Mm-hmm.
Yeah. Okay. All right. Anything else on this one? I realize we've spent all the time on the IBM one, but it's been a good discussion and it is relevant to the other ones as well. We've not really touched on the power side. I'm trying to talk to a few of the power supply companies, seeing if I can get their involvement in helping us bring the power tree together for these modules, and if they want to be featured on there. So I'm trying to see if I can get some support there for the work group. So ongoing conversations. If any of you know any power companies or anybody specific that you think was going to be very helpful, then please let me know if you've got any contacts that may be interested in helping us out here. So I just wanted to go onto the FPGA one quickly while we've got a few minutes left. So let me start. So this the Xilinx device. The nice thing about the FPGAs is they can talk anybody's language. So we're actually protocol agnostic, or pretty protocol agnostic, even at the silicon level. And it's your bit stream that actually turns you into the protocol specific. So as a colleague of mine once said, that the FPGA is the wonderful universal joint. This would allow us to connect an NV link to an SMP, you know, provided you can get the IP from the various vendors. But it is quite an attractive universal joint, and certainly between open standards. And so that makes it extremely attractive when you're building these heterogeneous systems that otherwise might not like talking to each other. So it's great for that and great for experimentation, as well as all the other acceleration features and architecture fun that the FPGAs bring. But we do have a decision to make, because there are some specific ones which are critical, the PCI buses. And you can see on this topology, I've got the PCI buses going to the standard EDSFF connectors, and which means, because we have the number of physical lanes we've got, does limit us with the hard PCI to only 4 lanes on these last 2 connectors. I then showed this architecture, which was maximizing your memory to go along with this example, where we had 8 terabytes of memory on 32 OMI channels. But then that would necessitate really putting the PCI onto the near stack connectors, which are topology connectors. And that would stop you from being able to plug in NVMe drives or things like that into this. So I'm sort of thinking that we might want to go with this topology. Is where my head's going, and sacrifice a couple of potential memory channels, or we may be able to jig things around to still support that. But so this is the one we're going for. So just for people, this may be a bit of an eye chart, but hang on. Just for people that are not aware of the device we've chosen, the device we've chosen is the Versal Premium, which is the highest end family of the Versal family from Xilinx, and we've chose their biggest device. Which is the VP1802. So this is a humongous device, over 3 million, logic gate systems. The claim is over 7 million system logic cell system gates. The attractive thing here is you've got a total of 168 transceivers, so we've got a good transceiver count that can use up a good chunk of the I/O that we have on the HPCM. Still around 50 to 60%. But and that some of those I/Os, the 140, can actually be reduced to 70 and actually go at 112 gig. So if you do want to communicate at 112 gig, there's that possibility here as well. Just as I was mentioning, on the PCI bus, you can see it's Gen 5, and it does they're by 8. The hard IP that they provide is 8 lanes and 4 lanes. So they've got a total of 4 PCI buses, 2 being 8 and 2 being 4. Then on the other channels, you've got various things you can do with Ethernet, etc., interlacking, and so as well as soft IP for all the other different standards like CXL or OMI, etc. And just on the package front, basically this big device comes in one package, which is a 65 millimeters by 65 millimeters in this particular footprint. Okay, so basically, I'm favoring this format where we keep the PCI lanes on the EDSFF connectors, and that really does allow us to be flexible between cabled I/O for PCIe or various PCI modules, or NIC 3.0 or an NVMe drive, etc. So you can still plug those in and natively leverage this, as well as cabling over to the host interface board. But that would sacrifice the number of memory channels we could have if we went with this one. Well, the PCI buses could run OMI or CXL as well, but obviously you would sacrifice being able to plug an NVMe drive in, for instance. So, or have a host connection, which you obviously want at least one of these to give you a host connection. So, so this is the one I'm proposing that we actually move forward with. And then, yeah, that's really it. Obviously, we've got the other conversations like the IBM one, the system management. It's the same questions go on here, but we probably treat this one more like a. Well, should we treat this more like a purely an accelerator needing a host, or arguably, actually, I think we should treat it as though it could be a host as well. I think in all of these, they've all got processors in them now. Even these accelerators, they don't really need a standalone CPU for their management anymore. So I'd like to make this a truly heterogeneous platform. So every module we design it so that it could be the main processor, as well as it being purely just an accelerator relying on other processors. So we're looking at this as peer processing is where my head's going. The next thing really is to make progress on this. If anybody's got any feedback on the interconnect options here, then I'm all ears, because that's the only thing that I think is going to dictate how we go forward here. With this configuration, that we'd probably limit ourselves. We'd have to drop probably at least 2 channels of OMI. So, which we've got 32, so you'd go down to 30 or maybe 28 channels of OMI in this configuration. So maybe that's not too much of a hardship for the extra flexibility. Okay, any final questions on that?
Alan, who is going to support this project to build a prototype?
All of this, that's exactly what I'm trying to find members that can contribute their own effort and maybe bring some dollars to the table. But we're also talking to the government bodies that find this quite intriguing. And so Trent, and I think Trent from Lawrence Livermore isn't on, and nor is Bob from NASA. But I've been talking to them and another guy I know from Oak Ridge National Labs in terms of whether we can actually get funding for these individual projects, and whether you as a group can say, I want to help this, and you could apply for that funding. I'm trying to get a funding package together, because normally they need a big prime, and but I'm saying OCP should be the prime sort of thing. So I've actually I've emailed the management of OCP and said, hey, could we be like the program manager of this, of trying to pull these pieces together and making sure everything is cohesive? And then, but some of the POC efforts could be separately applied for funding. And so I'm trying to get the government to talk about how do they go about making this happen, rather than their traditional approach to HPC, which is going to the prime or assigning a prime that's already an incumbent and has a vested interest in tilting the universe in their direction. And every supercomputer we get, it's a fresh design from scratch, whereas we're trying to say this would be a building block so that, you know, we can progress supercomputers without having to have a brand new piece of hardware every few years of cycle. So I am trying to get funding there. I'm hoping the bigger players here, that maybe the likes of IBM and Xilinx and AMD can actually say, oh, we quite like the look of this. We'll help to build a module with our version. And if we can get two or three of the bigger vendors making a module with their technology, then hopefully that'll be a bit of gravity to pull everyone else in and say, actually, this is looking interesting and helping us out on the other aspects. So I'm trying to get a little bit of independent momentum, and I'm trying to convince government funds to help make this happen in the interests of our industry.
Great. Since we, that we are in our torment, can look at into work as a partner with the IBM on the power 10, and also in the memory disaggregation world for this HPC. So let me know or keep me posted.
Okay, yeah. Well, so I'm early days there. I don't know. I'm not a funding guy, so it's not exactly my skill set. But I'm trying to attract people that I'm hoping OCP might see the value of this as a whole, and you know, so participation from the members here, you know, from you guys that are with the bigger organizations, if we can get some momentum here, then it probably makes it more attractive for government support as well, because of its openness, and so that's what I'm working on. So if anybody is really well versed in funding land and how to attract this and how to apply for these various funds, I could do with some skills that know the legwork.
I can probably introduce you to some people for that one.
Okay, Kevin, thanks.
And I have contacts as well, Alan, at the national labs that can maybe help out. So let's talk later.
Yeah, and I think in that sense, if maybe like IBM's obviously one of the traditional primes, right? so you're really well versed in doing it, but yeah. So if we know how to do that, but we can do it in a much more of an open fashion rather than you know, so that IBM isn't the prime anymore, or HP is not the prime anymore. It's a case of it's a club. The prime is a club of collaborators within OCP. And IBM could get a chunk of money from the government to do their help with their modules, their contribution, and Xilinx could get a chunk for their contribution, and AMD for theirs, etc. But they're treated as individual contributors rather than a single prime. Is where I'm going.
Yeah, and I think that's a good idea, and I would think the government would be, the DoD would be very interested in this, simply because, like you say, there's a huge bill every time we want to turn the crank, and it's all about, you know, infrastructure and things. When if you could like standardize this, and you know what we really want to do is maximize the processing power that, you know, and the throughput, which you could do with this without having the big bill of every vendor having their own, you know, solution. I think that would be very attractive. So yeah.
And without having to go to ground zero, like Stephen Roberts presented for me on a couple of summits ago on the topic that they start from scratch with all of the management side. You see, very new machine. They've got to start from scratch with all the monitoring. And
yep.
So that's a really important part of the system management, and I think that's where some huge contributions come there, which obviously IBM is doing a great job at contributing that to OCP as well. So thanks.
All right.
Okay, guys, I realize I've overran, but thanks. That was a very good discussion, and hopefully we can start to get the ball rolling on bringing these modules to reality. So I guess that's where I'd like to go next. So I think we continue the discussion next week. Maybe come with your questions, your feedback, your ideas, and let's keep the ball rolling. And by the way, these two modules are not the only modules. We can do any other module. Anybody, Intel can come in. You know, Samsung, you can make a module. You know, anybody. If there's particular favorites. In fact, Michael Choi, if you're, you know, I know you obviously CXL is huge to Samsung. If you want to come and build an Intel module with CXL on it, you know, if they're, the trouble with Intel at the moment is they only have parallel memory, which I can't support, so I can't do anything with a CPU from Intel. But maybe an FPGA from Intel with CXL on it, supporting the Samsung module would be great. So obviously, and the Xilinx one can support CXL, so maybe just this module with that side of things. But there's, you know, the idea is we're agnostic. Everybody can come and play in this.
Okay, thank you.
So I'd be delighted if other people want to build modules. I'm just trying to get two that I've got some traction on off the ground. Okay, all right, everyone. Well, thank you very much, and we'll try and make some progress here in the background, and hopefully we can discuss a bit further in a couple of weeks. So thanks very much, Joe.